All right, number 11. The blue ones are what element?
Nitrogen,
And the white?
hydrogen.
Hydrogen. So that's going to be N2H4. N2H4, how would you name that?
Dinitrogen tetrahydride.
Yeah. Dinitrogen tetrahydride. N2H4. There's another name for this. There's a common name. But what would you say about this? You know, well, let's look at the redox properties of N2H4. Would you say it's electron rich, electron poor, or somewhere in the middle?
I'd say it's a little rich.
A little rich, okay. And what are the oxidation states here?
Hydrogens are +1, nitrogen is -2.
-2. So yeah, that's pretty rich because the max it could have is -3. And so it's pretty rich. And so we're going to react that with, what's that molecule there?
N2O4.
N2O4. And what could you say about N2O4? Well, one, let's name it. It's
Dinitrogen tetraoxide.
yeah, dinitrogen tetraoxide. Except sometimes they'll just call it tetroxide. Drop the A in tetra. Dinitrogen tetroxide. What would you say about this in terms of redox properties?
Well, the nitrogen is very poor.
Yeah. So this is going to be -2. This is going to be -8. And this will be +4. That's pretty poor. It's not max. The max would be +5. Yeah. And so what we have here is, I would say this would be a pretty decent, what? Oxidizer or reducer?
Reducer.
Oxidizers are electron poor species or electron rich species? The oxidizers that we encountered.
Poor. They take them, right?
Yeah, oxidizers take electrons, so they're poor like oxygen. You know, O2 doesn't seem so poor, but it's poor because it'd rather be oxide rather than oxygen. And so this would be an oxidizer, this would be a reducer. Electron-rich species are reducers. Reducers are fuels. Electron-rich species are fuels. And this is called hydrazine. Hydrazine is rocket fuel. And so, but we're not going to oxidize the rocket fuel with oxygen. We're going to oxidize the rocket fuel with dinitrogen tetroxide. Okay. And so there's some reaction here. And in this reaction, what do we form? N2 and H2O, so from H2O and N2. N2, the oxidation state is 0. Elements in elemental form are 0. And so some nitrogens lost, some nitrogens gained, and it all balanced out to a 0. And so these nitrogens lost 2 electrons each, but these nitrogens gained 4 electrons. So it wasn't quite balanced. Well, no. Yeah, it wasn't quite balanced. But anyway, we got to balance this, write a balanced chemical equation for this. If we have all the reactants and all the products, then we just switch the numbers around. If we don't have all the reactants and products listed, then what we do is we balance this according to skeleton redox. And what we do is one of these, lost And so an N2H4 lost, and that's going to lose it to N2. The other one gained. And so this one, N2O4 gained, and they form the same product. Water, we don't care about because those balance in the end, you know, in this case. And so one of these will be our, what we call our oxidation half reaction, this one, it's losing. This one will be our reduction half reaction. So we can balance it this way by a skeleton. That's if something's missing, but if this is all there is, then we'll just try to balance it by adjusting the atoms. In redox, we don't normally balance it this way. Redox reactions, because they're a little bit tricky in terms of balance, if we balance it by atom, we have to balance it by atom and oxidation state. In other types of reactions, we can just balance it by atom, like acid-base or metathesis. But for redox, it needs to be balanced by atom and oxidation state. And the reason, this is skeleton here. The reason we don't normally balance it by atom is because it doesn't always work. So for example, you know what silver ion, silver ion is actually an oxidizer. Silver metal is more stable than silver ion. Silver is a coinage metal. And silver ion wants to take electrons. It's an oxidizer. And so it can take electrons. So for example, it can take electrons from zinc, solid. In what forms here? Yeah, zinc ion and silver metal. And then when we look at that, does that look balanced to you? Yeah, it looks balanced. One silver, one zinc, one zinc. We're done, right? No, we're not quite done because we shouldn't balance redox just by atoms alone because we could be missing something. In this case, we are missing something. And you can see we got to be missing something because the charge on the left, which is +1, doesn't match the charge on the right, which is +2. And so we don't see what's happening with electrons here. And so this is why we got to balance by atom and oxidation state. If we were to balance by atom and oxidation state, we actually need 2 silvers. Now it's balanced. Well, the same thing happens over here to some degree. It could happen, you know, similar type situation where something's not quite right with electrons because in redox reactions, electrons are not fixed to a particular atom. There's electron transfer.
So to balance the oxidations, do you have to do full skeleton, or can you just balance the atoms and then look at the oxidation state?
You could do that. Yeah, you can balance out the atoms, look at the oxidation state, and make sure things work out. You know, in this case, it would have worked out because we have all the species present. And so if we had balanced this, figured it out. There are 2 methods to balancing redox. One is a skeleton, and the other is what I just said here. And if you pay attention to the charges, you can figure it out as well. Oxidation states are the parent charge. So how would we have predicted this? You know, this would have been kind of hard to predict. You know what exactly forms because it depends on the conditions. You know, maybe we would have formed some other oxides of nitrogen during this redox process. But in this case, water's stable, nitrogen's stable. In other reactions, we might not have that. So let's take a look at number 12 here. Number 12 is, what's the first molecule? ammonia. Ammonia, is that electron rich, electron poor, or somewhere in the middle?
Very rich.
Yeah, this is rich, as rich as nitrogen is going to get, -3 plus 1. And so this is a good fuel. In other words, you can burn ammonia quite easily. And what's the other molecule?
O2.
O2. So we're going to take ammonia plus O2. In other words, rather than using N2O4, here we didn't even need any oxygen because we had N2O4. N2O4 is going to be an oxidizer. O2 is an oxidizer. And so what should we form here? Well, maybe we're going to form some N2 and H2O again, right? But we didn't. What did we form in this case?
H2O.
Yeah, H2O
And
and NO. The structure for NO is wrong in this. You know, here they show nitrogen, hydrogen single bonds, trigonal pyramidal. This is an oxygen-oxygen double bond, oxygen, hydrogen single bonds. But in NO, the nitric oxide, we don't have a single bond. NO has actually a triple bond. There. So it should have shown a triple bond, like the N2 above it. Right, it's just a different set of conditions. A different set of conditions yield, different products. And so this is the advantage of skeletons, because sometimes it's hard to predict these. You just got to mix it together and see what happens. In skeleton, we mix it together and see what the products are. And if we need to balance it, we can balance it by the skeleton redox method here. And same thing here. We mix it together, and so you burn ammonia, you form nitric oxide. Is nitric oxide complete combustion of the ammonia? No. What would complete combustion of ammonia be?
N2O3.
Not N2O3. N2O3 would have nitrogen plus 3. It would be N2O5. This would make nitrogen plus 5. But maybe, the conditions weren't severe enough to do that. Nitrogen plus 5 is quite reactive. It's not so easy to make. And so again, another skeleton redox. The skeleton redox here. But in normal skeleton redox, they don't give us things like water. We'd have to figure it out, like O2 goes to the blank, question mark. In this skeleton redox, they're giving us everything, so we don't necessarily have to use the skeleton method. We can just try to balance it by atom. And 11 and 12 just work okay balancing by just atom. There are no other reactants like H plus in there that we have to worry about. So this is just some exercises in balancing, but the technique that we're using to balance isn't the best technique for these types of reactions. And oxidation of some electron-rich nitrogen compounds here, using 2 different oxidizers. Okay, what's next? It's like 18 is next. Iron metal, is that, would you say electron rich? Electron poor or just happy as is? In other words, I'm asking you this. You know, we know metals can be oxidized. Is iron easy to oxidize or hard to oxidize? Easy to oxidize. Everything rusts. Since it's easy to oxidize, then we would consider it electron rich or electron poor?
Electron rich.
Electron rich. And so this is electron rich. How about water? Is water electron rich, electron poor, or just happy as is? It's happy as is. Water is pretty stable. That's what we call standard. Under standard conditions, under normal conditions, water is pretty unreactive. Would you expect water to oxidize iron? Well, water is both an oxidizer and a reducer. So when we look at the oxidation states, it's not the oxygen in water that can oxidize. Oxygen already has 2 electrons. It's got a complete octet. It's -2. But hydrogen is +1. So it's the hydrogens in water that might oxidize iron. But I wouldn't expect this to happen under normal conditions, but this is not under normal conditions. A commercial method of manufacturing hydrogen involves the reaction of iron and steam. So it depends on the temperature of this steam. You know, if you have a high temperature steam, it's going to be much more reactive than just liquid water. And so in this case, under these more extreme conditions, and what is that temperature? Well, right now we just have delta. What we have to do is we have to figure out what that temperature is. You know, is it right at 100 degrees C, or do we need a much, much higher temperature than that? Maybe 150 degrees C, 200 degrees C, some superheated steam. What is it? And so this is, again, the two-pronged approach here. It would be nice to just go ahead and calculate it. My calculation says that at 139 degrees C, it's not enough, but at 140 degrees C, it's just right. But that calculation is very difficult to do, so what people do is they just try a whole bunch of different temperatures, a whole bunch of different pressures, you know, high pressure steam, low pressure steam. Does it all work? And so they try a bunch of these things and then see what happens. And so in skeleton, we need to know, you know, what did it form? I mean, we could take some guesses. What would you guess? You would guess oxides or something of, or even a hydroxide of iron. You know, so it's some kind of iron-containing compound. In this case, they do it, and then they figure out, you know, they form some of this, Fe3O4, solid, and hydrogen gas. This is not balanced. We're just looking at the reaction here. So water was capable of taking electrons. When water takes electrons from iron, it goes to the hydrogen. And so the hydrogen goes from +1 to, what's the oxidation state here? 0. So each hydrogen gained 1 electron. And then iron's going to lose electrons. And so what is this? Is that iron 4 oxide? I'll just bring this over here. Iron 4 oxide? No, it's not. Is that iron 3 oxide, rust? Rust is iron 3 oxide or ferric oxide. No. Does anybody recall the name of this stuff? Most people call it by its common name. What is the common name for this? Magnetite. And what's special about magnetite? Do you know the charges on iron and magnetite? If we look at magnetite, we have 4 oxides, let's say. That's going to give us a net charge of -8. And then we have 3 irons. These 3 irons have to have a net charge of +8. Because +8 -8 is going to give us the net charge of the compound, which is 0. And so we need to distribute +8 over 3 irons. What is it? Well, if we distribute them evenly, it would be plus 8/3. Plus 8/3 plus 8/3. So plus 8/3 plus 8/3 plus 8/3 gives us plus 8. But are we going to distribute it evenly? Do you know what we did here? Did I tell you what we did for this?
Yeah.
This is plus 2 2/3. And so I guess you could call this iron 2 2/3, which would be the same thing as 8/3, because this is going to be plus 8/3, plus 8/3, plus 8/3. And so this would be iron 2 2/3 oxide. Does that sound right? No, it doesn't. And so instead, you know what this is? It's not this. It's not the average. It is going to be,
Plus 3 plus 3 plus 2.
yeah, iron plus 3, or 3 plus, iron 3 plus, and iron 2 plus. And if we combine all those, that will give us the desired plus 8. And so this is how we're going to generate plus 8 over 3 irons. 2 of them are going to be iron 3, 1 of them is going to be iron 2. So would you say that this was complete oxidation of iron? Normally when we have complete oxidation, it goes to iron plus 3, rust. It could go higher, but those are quite unstable. And rust is pretty stable, so it seems to be iron 3. And so 2 of the irons were completely oxidized, but 1 of the irons wasn't. 1 of the irons only got to plus 2. It didn't quite make it all the way to plus 3 under these conditions. Maybe if they added more heat or did something, greater pressure, then maybe we would have had iron 3 oxide rust, and iron would have been completely oxidized. Completely oxidized meaning completely oxidized to its common, form, rust. Iron could potentially lose a total of how many electrons could iron potentially lose? Well, it has 26 electrons. And what's the nearest noble gas? Nearest noble gas would be argon. So to go from 26 to 18, we'd have to lose how many? 8 electrons. That has the potential of losing up to 8 electrons. But losing up to 8 electrons is hard. I mean, even losing 4 electrons, how many plus 4 cations do you know? Plus 4, it's hard. And so this is why it kind of maxes out at plus 3, because if you try to get this to plus 4, it's going to be extremely difficult energetically. Even though, in theory, it should be able to go all the way to plus 8. That's plus 8 for each iron. Which would give us plus 24 net if I had 3 of them. All right, so this is another redox reaction. This is just showing non-standard conditions, non-standard thermodynamic conditions. Water's reactivity is going to change depending on its temperature and pressure. That's steam, actually. This is just a straightforward dimensional analysis. How many grams of hydrogen can be produced from 87.2 grams of iron and an excess of water? So limiting reagent's iron. Just use that to stoichiometrically calculate how much hydrogen. This is a balanced chemical equation. How many grams of water are consumed in the conversion of 25 grams of iron to magnetite? Okay, just another straight stoichiometry problem. If 29.2 grams of hydrogen is produced, how many grams of magnetite must also be produced? Another straight stoichiometry problem. So after 18, we're looking at 22 next. The reaction of potassium superoxide, KO2. It looks like peroxide, doesn't it? What's the difference between peroxide and superoxide? They're both O2. Peroxide is O2 charge, 2 minus, O2, 2 minus. But superoxide is O2 charge, minus. That's why there's only one potassium here. And so this is the superoxide ion. What's the oxidation state? Superoxide. Yeah, negative 1/2. Each oxygen must be negative 1/2 to add up to a total charge of negative 1. And so it's likely that one of the oxygens is 0, the other is negative 1. But anyway, is it happy, do you think? What do you think? Superoxide, is that electron rich, electron poor?
It's 4 for oxygen.
It's poor for oxygen because oxygen wants to be not negative 1/2, it wants to be negative 2. Okay. So if we take the potassium superoxide and then react it with carbon dioxide, what's going to form? Now, if you look at carbon dioxide, is it very reactive? It's not very reactive. It's a greenhouse gas, so it gets a bad reputation, but you exhale it with every breath. And it doesn't seem so reactive, right? It doesn't cause you too much distress. Yeah. But looking at carbon dioxide, we know this is +4, this is -2. So it's maxed out. Would you call this electron rich, electron poor, or what? I call it electron poor, but not terribly poor. I mean, it's +4, so it's at the extreme end for carbon. But is carbon dioxide a very good oxidizer? That's the question. No, it's not that reactive. It's pretty stable stuff. And so what's happening here? What's happening here is we're going to form some potassium carbonate and O2. And so what's happening? Well, what's happening is in carbonate, potassium is +1, oxygen is -2. That's +2 -6, that's -4, therefore carbon's +4. Did anything happen to carbon? No, nothing happened to carbon. Did anything happen to potassium? No. And so what happened here? Okay, this oxygen's -2. This oxygen is 0. So what must have happened is that normally we don't even think of this as electron rich, right? This is just happy as is. Oxygen likes to be -2. But then you have this oxygen, which is terribly unhappy because it's only at -1/2. And so these two oxygens are going to go at it and react. This oxygen wants more electrons. This oxygen doesn't want to give up any electrons. And so what's going to happen? What's going to happen is, how many oxygens am I going to have? So this is unbalanced here. I guess I could work at balancing it. Should we balance it? All right, I'll balance it. 1 potassium, 2 potassiums here, so we'll need 2 KO2s. And that's 1 carbon here. And so that gives us 4 oxygens plus 2 oxygens, 6 oxygens. And so 3 oxygens plus 3 oxygens will give me 6. So I'm going to call this 3/2 an oxygen. And so I can get rid of the fraction by just multiplying everything by 2. So let's go ahead and do that. So this is going to be 4, this is going to be 2, 2, 3. So what's happening is this. I have these oxygens, 4 of them at minus 1/2. That's the average, so I'll just leave it like that. And then I have 4 of them at minus 2 in CO2. And so normally this oxygen won't lose it, but this oxygen was very unhappy. And I'm going to end up with 6 at minus 2 here. 4, 5, 6, and 2 at 0.
We have 6 and 0.
Oh yeah, 6 at 0. 3 times 2. So what happened here? What happened here is, okay, we'll take these 4 and just leave those alone. I miscounted.
We have 8 at negative 1.
Oh, right, 8 at negative 1/2. So I guess the compromise here was, let's see, 1, 2, 3, 4, 5, 6. So 6 of these, 1, 2, 3, 4, 5, 6. 6 of these will lose a half of an electron each. So that's going to be 1 electron, 2 electrons, 3 electrons. And then these ones are going to gain those 3 electrons. And so this one gains, this one's going to lose. Something like that. So it's kind of bizarre because the oxygen here will oxidize that oxygen over there. In other words, the superoxide is going to oxidize the oxide over here. Okay. It's a bit complicated because of this. You don't have to worry about this. This is just trying to analyze it. But it wasn't so easy to see. So forget it. All right, next. Do we have? Well, this is a very interesting reaction because if you look at this reaction, it takes CO2 gas and replaces it with O2 gas. And so it's used in life support systems to replace CO2. So if you're on a submarine or if you're like out in space, this would work quite nicely because you don't want the CO2 concentration to get too high. If the CO2 concentration gets too high, it becomes toxic. Okay, 23. So this is another just stoichiometry problem. 23, iron ore, and these, like the basic stoichiometry problems, you can get a review on those through the MESA. Did anybody attend MESA today? Okay. How many people are showing up?
I saw a group of 4, and it was me and another girl, and 2 more would be.
Okay, that's good. Iron ore is impure, okay, iron 3 oxide, Fe2O3. When iron 3 oxide is heated with an excess of carbon, coke, metallic iron and carbon monoxide gas are produced. So it turns out that oxide is pretty happy as is, but iron 3, this is only +3. And so you think, okay, iron 3 is probably pretty happy as well. But it turns out that iron 3 is surprisingly good as an oxidizer. And so iron 3 is right here, and what it means is iron 3 is a better oxidizer than what? Iron 3 is a better oxidizer than this oxygen. All this oxygen is producing hydrogen peroxide, so this one's not very good. We compare it to this oxygen here, which produces water. So iron 3 isn't as good as oxygen. It's not as good as silver ion, but it is better than iodine. It's better than copper 2. It's better than sulfate. And so iron 3 is a pretty decent oxidizer. And this is going to be reacted with a carbon solid. This is coke. This is kind of like a charcoal-like substance. Carbon is right in the middle. It's 0, so it could either lose or gain. In this case, it's going to lose electrons to iron 3. In that process, it's going to make iron the element, probably molten iron, but it'll live and cool down. And carbon monoxide. So the iron 3 is going to oxidize the carbon, but it's only going to oxidize it to carbon monoxide. It doesn't completely oxidize it to carbon dioxide. And so that's going to depend on the conditions. So we balance this equation here. This is redox. Another example of kind of a skeleton redox reaction, where we're told what the products, the major products are. From a sample of ore weighing 938 kilograms, 523 kilograms of pure iron is obtained. So from the kilograms of iron, we can go to grams of iron to moles of iron to moles of Fe2O3, and moles of Fe2O3 to grams of Fe2O3. Once we know how many grams of Fe2O3, then we can figure out what the percentage of this ore is Fe2O3. So that's a common stoichiometry problem, figuring out the percent composition of a mixture. And the percent composition of this mixture, nothing else should react. They say a sample of ore, okay, iron ore, was treated with carbon. And so in this particular mixture, only one species reacts. And that one species is the iron 3 oxide. You have other types of mixtures, like on the test. The mixture on the test, both species reacted with the acid in that case. And so if there's another species here that reacts with the coke, then we have a reactive mixture. That is a more complex mixture. But this one's not the case. Only one species reacts, and so it's straight stoichiometry. Okay, next is number 29. Without performing detailed calculations, which of the following metals yields the greatest amount of hydrogen per gram of metal reacting with HCl? So if we take a look at the metals, the first metal is sodium. So we have sodium reacting with HCl. Do you recognize this pattern? It's single replacement. And it sure would be nice just to be able to do single replacement with this. But we need to check, you know, the roles. For example, A should be the, what? A needs to be, in single replacement, if I have the A plus BX pattern, A's got to be the, or what's the role that we assign A to when we set it up in the single replacement pattern? Does A plus BX yield what? AX plus B. So what happens is A starts off as the neutral element, 0, and then it gets oxidized to a cation. This is going to be plus Z, whatever that is. Since I already used X, I'll use Z here. And B might have been plus Z, but then it's got to go neutral, and so it's got to gain. And so A, is it losing electrons in this reaction or gaining electrons? Losing electrons. And so a species that loses electrons we call what? An oxidizer or reducer? Reducer. And so A is a reducer. Is sodium a good reducer? You say? Is it electron rich? Sodium electron rich. No? Sodium metal. What's happened to it? What's the best reducer on the chart? Lithium metal. Lithium metal is the best reducer. It's on the bottom right of this chart, and it's on the top left of that chart. That chart's like an upside down one. Followed by potassium, calcium, sodium. Sodium's number 4. So would you consider a good reducer? Yeah. This is a powerful reducer. And so that makes sense. That seems to be properly assigned. The only other potential reducer would be X. X is what? Chloride. And so what's a better reducer, chloride or sodium metal? Sodium metal. Sodium metal reacts violently with water. Does chloride react violently with water? No. And in fact, you could eat chloride. A lot of people eat chloride when it's combined with their sodium chloride. What about water? What do you think is a better reducer, water or sodium metal? Sodium metal. So in this case, I'm starting to think, single replacement's okay. And then when we look at HCl, is HCl an oxidizing acid or is it a mineral acid? Well, when we look at acids, acids we'll just call HX. X is the anion for this. We have two types when we're thinking about redox chemistry. We have the mineral acids. The mineral acids, X is equal to things like chloride, bromide, acetate, etc. What do all these species have in common? What those species have in common, they're all reducing agents. You know, they all have electrons that they might lose. Some more easily than others. For example, bromide loses electron much more easier than chloride. In oxidizing acids, X is equal to things like nitrate, sulfate, chlorate, perchlorate, etc. What do all these species have in common?
Oxidizers?
Yeah. All these are electron poor. And so these are kind of electron happy as is, or let me put rich in quotation marks here. They're not oxidizers. Down here, these are electron poor species. And some of these electron poor species are better oxidizers than H plus. So mineral acid, the only oxidizer present in mineral acid is H plus. And that's what we want because here, A is the reducing agent, B is the oxidizing agent, and X is the spectator. And so if I have a mineral acid like HNO3, then H plus should be the oxidizing agent and nitrate should be the spectator. But look at the rank. Here's H plus, where's nitrate? Do you see nitrate? Yeah, it's at the very top, which tells me that nitrate is a much stronger oxidizer than H plus. And so in a mineral acid, in terms of redox properties, we're just looking at H plus. H plus is the strongest oxidizer around in a mineral acid because these don't want to oxidize anything. These are going to be reduced, if anything. However, in oxidizing acids, it's not a spectator. X is a more powerful reactant than H plus. And so if I had HCl here, this is perfect. This works great in single replacement reactions. But if I had HNO3 here, no, this is not going to work great because nitrate, is nitrate going to want to spectate? No, because nitrate is a much better oxidizer than H plus. Does that make sense? Yeah? No? And so this is just to draw a distinction. And so if we have a mineral acid and we're oxidizing a pretty strong oxidizer, if we have a mineral acid and we're oxidizing a pretty strong reducer, something that's even better than water, the other thing is water. Will water react? Yeah, potentially, but water is very stable. And so here, when we look at our oxidizer, H plus, that's way better than water. When we look at our reducer, sodium metal, that's way better than water. So we don't have to worry about water reacting. And therefore, this should work. And so we expect to form sodium chloride and hydrogen gas. What does well, let's balance this. I'm going to just leave this as a fraction here. It might be a little easier to leave. Okay, about how much, what does a mole of sodium weigh? What's the molar mass of sodium? About 23 grams. So if I had a mole of sodium, that's about 23 grams of sodium. How much does a half mole of hydrogen weigh? Well, 1 mole weighs 2 grams, so half a mole weighs about 1 gram. So 23 grams of sodium will produce 1 gram of hydrogen. Okay, let's see what the next one is. I don't know if that's too detailed, but that's what I do. Magnesium. So again, magnesium is a pretty good reducing agent, and I'm just going to do single replacement for this. It's going to form magnesium chloride plus hydrogen gas. So the advantage of single replacement is fast. It's a mineral acid, so we're okay, and plus this is a good reducing agent. What does a mole of magnesium weigh? A mole of magnesium weighs about 24 grams. So this is about 24 grams. And it's going to produce how much hydrogen? Well, rather than a half a mole of H2, it's going to produce a full mole. Each hydrogen weighs 1, so this is going to be about 2 grams. So per gram, which one produces more hydrogen? Magnesium. You're going to get about twice as much hydrogen from sodium. And then we have aluminum next. Let's take a look at aluminum. Aluminum is going to require 3 HCl, and it's going to form aluminum chloride. and hydrogen gas. It's going to have to be 3/2 hydrogen gas, or 1.5 moles of hydrogen gas. So aluminum weighs 26, 27. So aluminum is about 27 grams. And we're going to produce 1.5 moles. 1 mole of hydrogen is 2, and then 1/2 mole is 1. So this will be 3 grams. No. So far, which one produces the most hydrogen per gram? Aluminum, yeah. And then finally, zinc. Zinc is going to combine with 2 HCl's, form zinc chloride plus H2 gas. Zinc, a molar mass of zinc is about 65 grams. And so this is going to be about 65 grams. The 65 grams is only going to produce 2 grams of hydrogen. And that's not much hydrogen at all. And so aluminum is it. What are the molarities of the following solutes? Sucrose, urea, methanol. Can you burn sugar? Sucrose? Sucrose is table sugar. And yeah, it burns. Sucrose is what type of organic compound? Carbohydrate. And the hydrate, what's the origin of hydrate? Why do they call it carbohydrate? There's no water there. You know why?
The hydrogen-oxygen ratio.
Yeah, the hydrogen-oxygen ratio is 2:1, like H2O. But there's no water in there. This is not like 10 waters or anything like that. Okay, let's take a look at the oxidation states. Hydrogen goes first, +1, then oxygen. So what do we have here? +22 minus, which means carbon must be 0. Sugars, do they burn easily? Yeah, sugars burn easily. So this, I mean, you know, even though it doesn't look electron rich, this is electron rich. You know, this is excellent fuel. And it's a good reducing agent. It's right in the middle though, because the carbon goes from -4 to +4. So it could go either way, but this one I would suspect would go towards the positive. You know, when we burn sugar, we're going to burn it completely to CO2. Does urea burn? What do you think? If you threw urea into the fire, could you burn it? No? Is it maxed out? Let's take a look. Let's do the oxidation states for urea. Which one goes first? +1. And then which one? Oxygen at -2. And then nitrogen at? What's nitrogen's preferred charge? Not -2. Not +3. Nitrogen can gain 3 or lose 5. And so -3. And then that means carbon has to be the loser. And so what does carbon come out to? +4. Well, this is +2 times 2 is plus 4. Plus 4 minus 3 times 2 is minus 6. So plus 4 minus 6 is minus 2. Minus 2 and minus 2, I guess you're right, plus 4, huh? Plus 4. So could we burn this part of urea? No. But we could burn another part of urea. What's the other part of urea that could be burnt? This part of urea can be burnt. And so if we try to burn it, you know what we're going to form? If we combusted urea and oxygen, it would burn to form, that's complete. It would burn to form CO2 plus NOx. And ultimately, if we could go full, complete combustion, it would go to N2O5. As we'd go from minus 3 to plus 5. But getting that plus 5 is difficult. So normally it stops before then. You know? So typically when we do combustion of nitrogen-containing compounds, it stops at NO, nitric oxide. And then the nitric oxide can undergo further reaction to NO3. I mean, not NO3, NO2, nitrogen dioxide. This one's hard to get. That one. So I'd probably say it burns to NO, if it burnt. Because NO seems to be a common product. Or NO2. NO2 is wrong. But anyway, this is making up solutions and then calculating molarity. Molarity is moles per liter. Methanol. Is electron rich as well. Methanol burns the CO2 in water.
I have a question.
Mm-hmm.
Why does can you explain how the second half of the urea burns? Because if they all have their preferred oxidation states.
Yeah. It's like this. The situation is, okay, nitrogen would like to have 3 extra electrons. And so if we look at nitrogen, nitrogen has how many protons in the nucleus?
7.
7 protons. And normally it has 7 electrons. But that's not complete. It hasn't completed its shell. In order to complete its shell, it'd like to have 3 more electrons, and then it can complete its outermost shell, the valence shell. This is including both the core and the valence. And so what we end up with is this situation where we have 7 protons, and how many electrons? 10 electrons. And what happens when we gain, when an element gains electrons, what happens to its size? So for example, does it shrink? Let's say I go from chlorine to chloride. Chlorine to chloride. Does it shrink? So I'm at chlorine and then I form chloride, it shrinks. Or I'm at chlorine and I go to chloride, it grows bigger, or it stays the same size. What do you think? It expands. What's the reason for the expansion? The reason for the expansion is, it's like this. It's like the science fiction, the tractor beams or whatever. It's like, you have 7 protons trying to pull in the electrons. Now you have 10 electrons that 7 protons are trying to pull in. It's harder than 7 electrons being pulled in by 7 protons. And so what happens here is when we're at nitrogen, it's this size, but when we go to nitride, like N3 minus, it grows in size because it's too hard for those 7 protons to pull in the electrons close. Now, if it expands like this, then the electrons can get kind of far away. And those electrons that kind of get far away are easy pickings for oxidizers. So oxidizer comes in and plucks those electrons off. Well, you might say that the same thing happens with oxygen. But it turns out oxygen's smaller, a lot smaller, and it's more difficult to oxidize than nitrogen. And so nitrogen is a lot easier to oxidize than oxygen, even though they both have their preferred charge. Let's say oxygen's at -2, nitrogen's at -3. They both have the preferred charge. And then the same can be said about fluorine. Fluorine, you know, it goes like this. Because we go nitrogen to oxygen to fluorine. Fluorine's the smallest of those. Now when they take an electron, they'll grow. And I said about double in size. But even if this doubles in size, it's still fairly small. So that's another way of looking at it. In fact, it turns out fluoride and oxide are kind of comparable in terms of size. And so yes, it has its preferred charge, but it's getting harder to hold on to those. We can see this quite well in something like sulfur versus oxygen. If I look at oxide versus sulfide, oxide is not considered a good reducing agent. You know, in fact, oxide is very difficult to reduce. It's very difficult to oxidize, and therefore it's not a very good reducing agent. Whereas sulfide is a very common reducing agent. In other words, sulfide loses an electron quite easily, and so sulfide is known as a good reducing agent. But this is a very poor reducing agent. You know, the only reason we got this to react in one of the earlier reactions is because we had superoxide. Superoxide is very unstable. It wants electrons. And so this just has to do with size. You know, sulfur has a whole nother shell of electrons. And so sulfur is quite a bit bigger, sulfide, than oxide. Does that answer the question about?
Yeah, so it's just like, because it's bigger, it's just easier to pluck off electrons,
Yeah.
basically.
Exactly. Easier to pluck off electrons. That's it. Sulfur would like to hold on to those electrons. Just like oxygen. Uh, 36, ethanol. This is just, again, this is making a solution, 1.65 molar. This is a molarity calculation. 36B, concentrated hydrochloric acid. When you buy concentrated hydrochloric acid, the concentration is expressed in percent by mass. So concentrated hydrochloric acid is like 36.0% by mass. We're given the density here, and the molarity comes out to about like 12 molar, if we calculate the molarity. You can try out these calculations. If you have any questions on them, you can come back to them and answer those. (42) Which has greater molarity of ethanol? A white wine, which is 11% ethanol by mass, or the solution described in 4.7? So this is probably just easiest just to calculate the molarities of both. Just figure out which one's greater. Ethanol, is it electron rich or electron poor? What would you say? Rich. Ethanol is very flammable. It's highly flammable. So it's a good fuel. It's electron rich. 47. Given a 0.250 molar potassium, what's this called here? Potassium chromate stock solution. Stock solution, what's that? A stock solution is just a solution that you have laying around in the lab. It's not a standard solution. A standard solution, you know, takes work to make because you need to make that accurately. A lot of sig figs, that is, with high precision. The stock solution, these are just roughly made solution usually. Describe how you would prepare a solution that is 0.0125 molar on potassium chromate. This is a solution dilution. M1V1 is equal to M2V2. Except we have to talk about pipettes. You know, you guys use pipettes or grad cylinders and volumetric flasks. So there's an example in the book about how to do that. Multiple examples in the book. So solution dilution, let's move on, 51. Do you recognize this type of reaction? What kind of reaction is this? Double replacement. So this is AB plus CD. So silver nitrate plus potassium chromate yields silver chromate and potassium nitrate. Silver chromate, chromates, phosphates, and carbonates are all insoluble. So this is going to be a solid, except for group 1 ammonium. This is not a group 1 ammonium. And then all potassium and nitrates also soluble, so this is aqueous. So the driving force for this is precipitation. And so this is, I think, yeah, how many milliliters of 0.650 molar potassium chromate is needed to precipitate all the silver in 415 milliliters of 0.186 molar silver nitrate. And so we start off with milliliters of silver nitrate, go to liters. Then from liters we go to moles using the molarity. We go to moles of silver nitrate, then we go to moles of potassium chromate, and then from moles of potassium chromate to liters using the molarity here, and then liters to milliliters. That should take care of the solution stoichiometry problem. 60. A method of lowering the concentration of HCl is to allow the solution to react with a small quantity of magnesium. So this is single replacement here. This is good, this is fine because magnesium is a good reducing agent, and HCl, is that an oxidizing acid or mineral acid? This is a mineral acid, so single replacement should work here. And we end up with magnesium chloride and hydrogen gas. The problem with this method of reducing the concentration of HCl is that it's going to contaminate your HCl with magnesium chloride. But if you don't care about contaminating your HCl with magnesium chloride, then this should work. The hydrogen will bubble out, so we don't have to worry about contaminating the HCl with hydrogen gas. And so what we have to do is we have to reduce it by 0.023 molar. And so we would have 250 milliliters, which would be 0.250 liters for 4 sig figs. Then we can figure out how many moles of HCl we have to lose, because it's 0.023 moles of HCl per liter that has to be lost. And once we figure out how many moles of HCl needs to be lost, then we can figure out how many moles of magnesium we need to add, and then grams of magnesium. So another straight stoichiometry type problem with a twist. '61. This is our experiment 14, except we didn't weigh out sample of oxalic acid. It would have been easier. Instead, we made what we call an oxalic acid standard solution, and then pipetted it. But this would have been easier just to weigh individual samples of oxalic acid. And so Here we have a 0.3126 gram sample of oxalic acid requires 26.21 milliliters of particular concentration of sodium hydroxide to complete the following. You know what this is? This is standardization of sodium hydroxide using oxalic acid, solid. We did standardization of sodium hydroxide using an aqueous solution of oxalic acid. And we measured out the volume. But we did make a stock solution of oxalic acid from actually that stock solution was pretty precise. Yeah. So this is just a titration problem, 61. '66. Look at that. How many grams of hydrogen are produced by the reaction of 1.84 grams of aluminum with 75.0 milliliters of 2.95 molar HCl? So this is just a single replacement. Aluminum is a good reducer. HCl is a mineral acid, and so we'll get that. I think I had the equation written there earlier. Aluminum was a metal that yielded the most hydrogen per gram. So straight stoichiometry, 66. And then 70. Chlorine can be generated by heating together calcium hypochlorite and hydrochloric acid. Calcium hypochlorite, it's a formula like this. Sodium, do you know what sodium hypochlorite is? Sodium hypochlorite is bleach. Sodium hypochlorite solution is bleach. What do you think about calcium hypochlorite? Would it also be considered a bleach? Hypochlorites are going to be soluble. These are soluble salts. And so both of these yield hypochlorite. The reason why hypochlorite is a good bleach is not because of the chlorine. What's the oxidation state of chlorine in this? Actually, maybe it is because. Which one's more electronegative, oxygen or chlorine?
Oxygen.
Then oxygen should get its preferred charge. What is oxygen's preferred charge?
-2.
-2. And therefore chlorine gets what? +1. Is bleach electron poor or electron rich? Poor. It's poor because chlorine doesn't want to be +1. Chlorine wants to be -1. And this net negative charge here actually is because of oxygen, not because of chlorine. And so this is bleach. So it's an oxidizer. Calcium hypochlorite would be bleach as well. And this is going to react with HCl. When we do chemical reactions, we look for all three types. So if I have this combination, the first thing I would say is this is not a redox reaction. You know what type of reaction that is? That's a metathesis. If this is metathesis, this is an AB plus CD reaction. So this AB plus CD reaction is going to form what? Are we out of time? Yeah. What is it going to form? It's going to form calcium chloride and HOCl. Is there a driving force? Yeah, there is a driving force. We're going from stronger acid, HCl, to weaker acid, hypochlorous acid. But, you know, calcium hypochlorite, this is going to be bleach. And hypochlorous acid, this is going to be bleach because nothing changed with chlorine's oxidation state. All these have chlorine in the +1. Is chlorine happy in the +1? No. And so bleaches are oxidizers. And so this is a double replacement. There is a driving force for this. But there could potentially be a redox reaction that occurs as well. In an acid base. Well, this is an acid base because hypochlorite's a base. This is an acid. So this double replacement is both acid base and double replacement. And so let's look at redox. And the redox reaction they're saying is that chlorine is going to be generated here. And so what we're going to do is we're going to form some chlorine gas. So we're going to have, basically, we're going to have this. The hypochlorite, chlorine plus 1, plus chloride. Well, this looks like it's going to get in tug of war, and we're going to end up in a tie. But there's some other stuff going on here, and that is with the H plus. Because basically what we're going to have is the two H pluses is going to be water, and then we'll end up with chlorine. Actually, we'll probably just do it the way they have it here. And so we can kind of figure it out, but somebody already figured out. So this is an example of a skeleton type redox. And so we have calcium hypochlorite plus HCl yields chlorine plus calcium chloride plus water. And so we end up with a redox reaction. And so skeleton is you just mix it together and see what happens. But we're kind of figuring that we're going to get some kind of redox to occur. All right, let me talk briefly about lab. The lab, I'm going to change the objective for the lab. Experiment 18. When we look at the pre-lab here, they give you a series of reactions. And from this series of reactions, you can see which one's more reactive, which one's less reactive. And then when you see which one's more reactive, which one's less reactive, then we can rank them in terms of, in this case, strongest oxidizer on the bottom left. This is different than what we normally write. We normally write the strongest oxidizer, fluorine, at the top left. The old convention is you write the strongest oxidizer on the bottom right. Do you see fluorines on the bottom right in that chart? This is an entirely different convention where the strongest oxidizer is at the bottom left, but I guess it doesn't really matter. And so this is why we don't want to say left side, right side, or we don't want to say up or down. You know, we just want a position where fluorine is and where lithium is. And so the objective of this is to do these reactions and see which one yields product and which one yields no reaction. And from that we can generate our own redox chart. And so this whole experiment is doing these reactions, observing them, and then ranking the oxidizers here. So we'll generate this first one, and then we'll add some more, generate some more, and eventually we'll come up with this one. And come up with this one, so we're going to just rank them from weakest to strongest oxidizer. We're not going to do that here. What we're going to do instead is we're going to use the redox chart there to predict the products. And so this was purely observational, but we're going to try to predict if we have any reaction or not, if there's driving force. And so don't set up your notebook like this. We're going to do all these reactions, but we're not going to analyze them in the same way. I'll talk about how we're going to analyze. In fact, we aren't going to analyze it, we're just going to predict it. And so the reactions that we're going to try to predict are things like this. Silver nitrate plus iron 2 sulfate. You know, silver nitrate plus iron 2 sulfate, that looks like a double replacement, doesn't it? That's metathesis. But you know what? This is not a double replacement experiment. This experiment is called what is this experiment called? oxidizing reducing agents. You see? And so what we're going to see is we're going to see that some things like this can happen. And so we do have a driving force for this metathesis reaction, but in addition to this, we also have a driving force for a redox reaction. In fact, we could predict this one, using the chart, because hypochlorite is on our chart here at 0.89 volts, so we'll have to rank it up there. And chloride is on our chart. The reactions between hypochlorite and chloride, so chloride's up here. And so we can figure or predict what's going to happen based on our chart in this particular case. Some of these other redox reactions we looked at, we couldn't predict what the products were because they weren't on our chart, and some of them weren't that easy to figure out. Because, NOx, we get so many different NOx that might form. Other reactions are a lot more straightforward to predict. Okay, I'm going to hand back your exam today. Next week we're going to have a little nomenclature quiz. The nomenclature quiz is going to be just a repeat of the nomenclature questions you had on this test.